Okay, I want to talk about number 6 from the 2019 AP exam because it was mentioned by the AP this year, and it was a bit of a different question. It was a very different question from previous questions that they had asked, so I thought I'd go through it. There was definitely some very difficult pieces of it, and one piece that I just thought was actually completely unreasonable. But anyway, obviously that's just my opinion. But let's kind of go through this. So some of it's actually pretty easy. So let's see, we got functions f, g, and h are twice differentiable functions with g of 2 equaling h of 2 equaling 4. And we have this line that is tangent to both graphs at x equals 2, that at x equals 2. Okay, so this line right here is tangent to both graphs at x equals 2. So the first thing they asked us to do, let's make my pen a little smaller on this one. They ask us to go and find h prime of 2. And h prime of 2, that's actually very easy. And the reason I say it right, if this line right here is tangent to the graph at x equals 2, then the slope of that line has to equal the slope of the tangent line. So in other words, 2/3. Easy peasy. And then the next one's very reasonable. So let's look at the next one. Nothing that we haven't done before. So we have this function that we define as a of x equaling 3x cubed h of x. And we're asked to go find a prime of x. So let's start with that, a prime of x. So this is a product rule, right? We have 3x cubed is one function, h of x is a second. So we get 3 times 3 is 9. So this is 9x squared h of x, right? Plus 3x cubed h prime of x, right? So I use the product rule. Now finding a prime of 2, we get 9 times 2 squared times h of 2 plus 3 times 2 cubed times h prime of 2, which gives us 9 times 4. H of 2, we were told, was equal to 4. Let me just double check. H of 2 is equal to 4. So h of 2 equals 4. And then 2 cubed is 8. 3 times 8 is 24. And then h prime of 2 we've already found is 2/3. So we get 36 plus 8, 16, okay? Which is 60. So again, very reasonable questions. The next one was difficult. And the reason I say that it wasn't necessarily that it was unreasonable. It's that this was the first time this type of problem had ever really been seen. This is the first time they used a L'Hopital's. So it was definitely one that we hadn't prepared for last year, and we haven't actually seen this year either. So it's a good one to go and look at. So let's look at letter C. So we have this function h that satisfies this, where x is not equal to. It is known that the limit as x approaches 2 of h of x can be evaluated using L'Hopital's. And then we're asked to find the limit as x approaches 2 of h of 2. We're going to use that to find f of 2, and then we're supposed to go find f prime of 2, and then show you work the least answer. Okay, so let's start with f of 2. So we know a couple things. So let's look at our function real quick. We know off the bat, there we go. We know off the bat that L'Hopital's applies. Agreed? So if L'Hopital's applies, and we're trying to find this at x equals 2, right, then what I should be able to do is, if I plug in 2 into the numerator, right, I get 2 squared minus 4 is 0. So the denominator, in order for L'Hopital's to apply, the denominator has to also be equal to 0. In other words, 1 minus this stuff has to be equal to 0. And in solving that, we get f of x has to be equal to 2. So technically speaking, right, this was at 2. So we could have at this point plugged in our 2's here. And I'm just going to do that now because we were evaluating this at 2. Could have plugged in 2 here, I guess, if we really wanted to. I didn't do it. Hopefully you understand the idea. The idea, right, is I was plugging it in, L'Hopital's applies, so we knew it had to be a 0 over 0 situation since the numerator equaled 0, the denominator equals 0. So all we had to do was take the denominator, set it equal to 0. So we now know that f of 2 equals 2. Sorry, not 2, 1. Bad math. Okay, so f of 2 equals 1. Great. Now let's go find f prime of 2. Okay, so let's go find f prime of 2. So a couple things that we know. I'm going to do this I'm going to keep this in purple. So what are some things that we know? I'm sorry, I'm just kind of, I'm losing it here for just a second. Okay, well, let's start from where we were. So we know that h of x, let's try this. We know that the limit as x approaches 2 of h of x equals 4. And we know that because we know that h of 2 equals 4. Okay, so as x approaches 2, this limit equals 4. Now, what that also means, right, if we apply L'Hopital's, right, that means if I take the limit as x approaches 2 of this function, the given function, it has to equal 4. But they said L'Hopital's applies. Okay, since L'Hopital's applies, let's go and do L'Hopital's. So the derivative of the numerator, so this is going to be the limit as x approaches 2. So the derivative of the numerator is 2x. The derivative of the denominator, remember when we do L'Hopital's, take the derivative of the numerator, take the derivative of the denominator, is going to be 3 times f of x squared times f prime of x. Okay? Now, evaluating this at 2, we get this. And what does it equal? Well, we already know what it equals. It has to equal 4 because we were told that when we evaluate this thing at 2, it equals 4. So now we're just going to solve this, right? So let's see what we got here. In the numerator, we get 4, 3. Now we already know that f of 2 we said was 1, so this is 3 times 1. And we don't know what obviously f prime of 2 is because that's what we are solving for. Also, just a quick note, and you probably already see it, and that is that I made a slight mistake when I took the derivative of that denominator. This should be negative. Okay, so I'm going to fix that right. Hopefully you guys see that, right? When I took the derivative of that denominator, I should have had a negative number. So that was a mistake, but it's in there now. Hopefully that makes sense to you. Again, the idea doesn't change, just the math was a little bit off. Okay, so let's see what we got here. So this simplifies as 1, and this is 3 times f prime of 2 equals 1. So we end up getting, let's see, 1 equals negative 3f prime of 2. Divide both sides by negative 3, and I get negative 1/3 equals f prime of 2. So let's just kind of review that really quickly. For that second part, I'm going to review the first part really quickly too, but let's go backwards here. So in the first one, in this one that we're looking at right here, right, we knew that if we took the limit as x approaches 2, right, of h of x, we get 4. And why? Because we were told that h of 2 is 4. So we knew that. So that means by L'Hopital's rule, we knew what the limit was going to equal to. So we took the function, we said, hey, the limit as x approaches 2 of our function has to equal 4. Then we applied L'Hopital's. We took the derivative of the numerator and took the derivative of the denominator, knowing, right, knowing that when we evaluated this at 2, like we did in this third step, right, that we should be able to solve for f prime of 2. And that's what we did from there on out, is we just solve for f prime of 2. Okay? Let's move on. Actually, let's move on to D. Hopefully those two, all of C makes sense to you. And the reason I want to move on to D is the one that I feel, so C was rough, but it's a stretch question, sure. And it's the first time they had a L'Hopital's question, which made it rough. Who knows? Maybe they'll have a L'Hopital's again. I don't know. But D, I felt, was kind of unreasonable. And the reason is, I mean, it's not necessarily hard. Okay? And let's just kind of picture what's going on here, and I'll tell you why I felt that it was a little bit rough. So, we know that g of x is less than or equal to h of x, okay? We know that. So from 1 to 3, so let's say from 1 to 3. So let's kind of draw this out. So g of x is less than h of x. So this is, let's just kind of say this is g of x, and h of x is going to be above it, right? Except we do know, and I want to kind of make a note of this. I'll do this in purple. At 2, both of them equal the same thing. They both equal 4. So in other words, maybe the other graph, maybe h of x, and I'm just going to, maybe it looks something like this. That's a bad idea. Maybe it looks something like this, right? Hopefully that makes sense to you. And the only reason is we know at 2 they're both equal to the same value, but otherwise we can say h of x is greater than g of x. Now, they tell us that k of x is in between both of those functions from 1 to 3, right? So we have this third function, k of x, and they want to know what is the value of k when x equals 2? Well, k lies in between, right? But what happens when we get to 2? Since both functions equal 2 from up top and below, k has to be equal to 2, right? K has to be equal to because it's in between those. It's squeezed in between those. Those two things equal the same. So when we squeeze a function in like that, that's called the squeeze theorem, right? It's where, so the squeeze theorem is where you say, hey, this function right here has to be in between these two, and it has to equal this value because these two other functions are squeezing it, and there's nowhere for it to go. So in this case, the purple and the blue function are both going to 2. They're both equal 2. They both equal 4 at x equals 2. And because green is in between them, it too has to equal 4. And that's by the squeeze theorem. Like I said, I felt that was a little bit, we don't do squeeze theorem in AB. It's not a standard. So maybe they weren't looking for you to say squeeze theorem. Maybe they were just looking for you to say, hey, look, the first graph has to be above, the second graph has to be below, and this one has to be in between, and maybe not name the theorem. But like I said, I thought that was a bit unreasonable. Anyway, the big reason I really wanted you guys to see this one was for letter C, because letter C was definitely an unusual one.